Well, today our discussion is from the portion of fluid mechanics, or we can say that is the mechanical properties of liquids or the fluids. The very first topic is regarding the intermolecular forces, and it will be followed by surface tension and capillarity. All these concepts are interrelated. When we use this term intermolecular forces, we are referring to a container having liquid and assuming that liquid is made up of many molecules. The molecules are very close to each other. We find that in the liquids or in the fluids, the molecules are quite close to each other and their separation is nearly 10 to the power minus 6 to minus 7 centimeters. So this is the intermolecular range. And intermolecular forces are generally attractive in nature. So when the molecules are quite close to each other, they have tendency of attracting, and as a result of interaction, there can be deformation in the shape of the liquid. However, liquids maintain the shape of the container. However, gases also are supposed to be the fluids, and they also maintain the shape of the vessel. So, in the intermolecular forces, our main concept that will be the force which acts between the atoms or molecules of the different substances is known as the intermolecular force. This force is of two types. So when we say that the forces will be of two types, we are referring to cohesive forces and adhesive forces. Cohesive forces are the forces among the molecules of the same substance, whereas when we use this term adhesive forces, they are the forces among the molecules of the different substance, like liquid and solid, or it is in the form of liquid and the solid in the form of glass surface. And when we speak cohesion or cohesive force, it will be among the two molecules of the liquid. So these facts are to be discussed, and the same facts are to be explained in surface tension. That is, when we use this term surface tension, we are referring to that surface tension is a property of the liquid due to which it gets stretched, and surface tension is force per unit length. That is, its unit will be Newton per meter, and intermolecular forces are very effective between 10 to the power minus 6 to 10 to the power minus 7 centimeters. So these are of two types now. So we further proceed. Like in the figure, we are finding that in the right portion, there is some liquid and the molecule is within the liquid, and we are finding that the forces will be in all directions. But on the surface, we find the forces will be towards the one line, that is at 180 degrees, and under the water between the different molecules. And in the left side figure, again, there are many molecules, and surface tension means that the molecules are at the surface, and in between there will be attractive forces dominating. And same is the case when the liquid molecule is inside, and that liquid molecule has got the attractive forces working between the other molecules within the liquid. So now the next thing we have to go through with, one is the cohesive force. As I have explained earlier, in the cohesive force, that it is the force between the same substance. So the text will be like this: the force acting between the molecules of one type of the same substance is called the cohesive force. So when we use this term force, obviously the force will be explained either in dynes or newtons. Another is an adhesive force. So in the adhesive force, we find that the forces are between the different types of molecules or molecule of the different substances. So the context is the force acting between the different types of molecules or molecules of different substances is called the adhesive force. Intermolecular forces are different from the gravitational forces and do not obey the inverse square law. So when we use the term gravitational force, it is among the celestial bodies. So we find that the gravitational forces, they are directly proportional to the product of masses and inversely proportional to the square of the distance between those masses. But when we speak intermolecular forces, the intermolecular forces means that we consider the fluid or we consider the liquid, and that liquid is made up of plenty of molecules, and the forces among those molecules, they are called the intermolecular forces, and they are attractive in nature. However, they are not exactly the same as the gravitational forces. Now, in the given figure we are finding, there are two figures. So, in the right figure, the cohesive forces are demonstrated, that is among the molecules of the liquid, and adhesive forces indicated among the molecules of glass and the liquid. And in the left side, we are finding there is substrate and there is adhesive, and then in the lower bottom again it is substrate. So, the pink lines are indicating the adhesive forces, whereas slightly green lines or bluish type of lines are indicating the cohesive forces. So, adhesive forces are always among the molecules of the two different substances like glass and liquid. And when we speak of the cohesive forces, these are the forces among the molecules of the same substance. So, this is what the demonstration in figure, and the distance up to which these forces are effective is called the molecular range. The distance is nearly 10 to the power minus 9 meters, as I have explained, 10 to the power minus 7 centimeters. That is equivalent to 10 to the power minus 9 meter. Within this limit, they increase very rapidly as the distance decreases. However, it is not an inverse square law. The molecular range depends on the nature of substance. Now, nature of substance means that is whether container is a glass and it is containing water, or container is glass or it is containing mercury, or the container is glass and it is containing kerosene oil. So this is what the meaning of the nature of substance. So molecular range depends upon the nature of substance. Sphere of the molecular influence, we find, like in the figure we are finding, there are portions indicated like A, B, and C. That is, for B and C, the molecules are partially inside water or partially inside the liquid, whereas A is fully immersed inside the liquid. When the liquid is fully inside the liquid, it is obeying the Pascal's law. That is, liquid transmits pressure equally in all directions. So this is the concept now given. A sphere drawn about any molecule as center with the radius equal to the molecular range is called the sphere of molecular influence. All molecules within the sphere of the molecular activity of a molecule are attracted by this molecule. This is known as the molecular theory of surface tension. So this is indicated in a given figure, that is the sphere of influence, that is the inner molecule has tendency of influencing B and C. Now we come towards the concept of surface tension. As I have earlier explained, that the stretching property of the liquid is called surface tension. That is, surface tension is the property of the liquid due to which it gets stretched. The membrane gets stretched, and surface tension is calculated by force over length, and its unit is Newton over meter, and its dimensional equation will be calculated from force over length, that is mLT minus 2 divided by L. So this gives the dimensional equation of surface tension, where tension means a kind of force. Surface means we are involving the volume as well as area. So it is molecular phenomena. It is explained on the basis of molecular forces, as we have just now expressed. The intermolecular forces, they are attractive in nature, and moreover they depend upon the nature of liquid. When we use this term nature of liquid, we are referring to its specific gravity and the density. The free surface of the liquid behaves like a stretched membrane, but the surface tension in liquid does not depend upon the area of the liquid, while the tension in membrane increases as the area under tension increases. Now, here in the figure, phenomena of the surface tension is indicated. That is, molecule B is just well within the liquid, that is in water, and other molecule A is partially immersed in water. So what we are finding that B molecule is facing the tension from all sides. That is, it is obeying the Pascal's law. That is, liquid transmits pressure equally in all directions. Whereas when the molecule is at the surface, we are finding the downward forces there and the linear forces are there on the molecule A. The resultant force on the molecule well below the surface of any liquid is zero, because these molecules are attracted equally in all directions. This is what I have explained earlier, and this is called what the Pascal's law. And any system is in equilibrium only when its potential energy is minimum. So the molecules of that liquid will stay in equilibrium and their potential energies will be minimum. Now we are again finding the liquid surface. So here a molecule is well within the liquid and other is just on the surface. So the nature of forces, as we are finding, that the molecule which is within the liquid, it is transmitting pressure equally in all directions, whereas on the surface we are finding that the forces are linearly acting in the opposite direction, and then other forces are acting between the molecules of that liquid which is under the surface. The resultant force on those molecules which are on the surface of liquid is maximum and acts downwards. If a molecule is brought from interior of the liquid to its surface, work will have to be done against this force, and due to this reason, the potential energy of molecule lying in the surface is greater than the potential energy of molecule in the interior of liquid. Now, in this concept, like to have the minimum potential energy in equilibrium, the liquid surface tends to contract its area to minimum. So the text will be like this. In order to have the minimum potential energy in equilibrium, the liquid surface tends to contract its area to minimum, and due to this reason, surface tension is exhibited. The surface of liquid appears to be stretched. So here the explanation is why the surface of liquid is appearing to be stretched. That is because of the forces among those molecules which are well within the liquid or which are just on the surface of the liquid. The force acting in a perpendicular direction on the imaginary line of the unit length drawn on the surface of liquid is called the surface tension. So surface tension is mathematically defined as force per unit length. So force is in newtons, length will be in meters. Therefore, the formula of surface tension will be T is equal to F over L. F is the force and L is the length of the line. The necessary work required to increase the surface area of the liquid by unity is known as surface tension. So we have just gone through the various definitions of surface tension, but the idea is same in all the definitions. That is, the tendency of stretching the liquid to a particular area is called surface tension. So in doing so, stretching, the work is required and work is force into distance, and the force is obviously of the surface tension, that is force over length. Now delta W means small work done, that is equal to small area into tension, and small area will be delta A. And from this equation we get, that is the tension or the surface tension, that is the ratio of delta W over delta A. When we use delta along with these numbers, means we are referring to small work or the small area. Now, our assumption is that if delta A is 1 meter square and delta W is T, then we will say that surface tension will be equal to T over 1. Surface tension tries to minimize the area of liquid surface. So that is called contraction or the stretching of the liquid membrane. Unit of surface tension, as I have explained earlier, it is force per unit length, it is Newton per meter in MKS, and it is dyne per centimeter in CDS. So MKS unit is Newton per meter or Joule per meter square, that is work per unit area, or it is force per unit length. CDS unit is dyne per centimeter or it is erg per centimeter square. You can further remember that 1 Newton means 10 to the power 5 dynes and 1 Joule means 10 to the power 7 ergs. 1 dyne per centimeter is 10 to the power minus 3 newtons per meter. So it is 1 dyne per centimeter and the number is given in newtons per meter. Dimension will be M, L naught, T minus 2. So dimension for surface tension will be, that is force per unit length. So we will put the dimensions of force, that is MLT minus 2 divided by T, and then we will get the dimension as M1 L naught T minus 2.